We'd be curious to see. Well, I'll go get it when you guys are dinking around doing something else. And I can show you next class period. I'll get it set up for next class period because I've got a lot of stuff to show you next class. We have to go in a dark room for the next class period anyway. Okay, so we'll finish today, day 14, and then we'll have a quiz on it next class period. So it kind of pushes everything back a day, but that's fine, right? Okay, so we've been talking about emission spectroscopy, and do you remember, Andy, what this equation is trying to tell you? Since we're talking about emission spectroscopy, what was that chemical equation trying to tell you?
The energy of the photon,
Which is that's H,
HGH,
which is the H nu part.
the sample or molecule.
Yeah.
So it's trying to tell you that the sample is excited.
Yes, it gets into some excited state, right? That M is in its ground state, a molecule in its ground state, it absorbs some light of some particular frequency that only that analyte is susceptible to. I mean, there's going to be other analytes that might absorb that too, but you know, it's getting pretty specific here. And then it gets into some excited state. And the emission comes from where, Andrew?
Energy of the photon.
Energy when that excited molecule does what?
Moves around.
Well, if you want emission spectroscopy, that excited molecule has to
Absorb.
well, it did absorb to get excited in the first place.
Uh-huh.
But if you want emission spectroscopy, that excited molecule has to do what? Melissa, what does it have to do?
Go back to its ground.
It has to go back to its ground state, but to get there, it does what? It releases a photon. All right. Now, if it transforms it into heat, you're not going to see it. So that won't be emission spectroscopy. So that's a bad thing. You don't want that to happen, right? But almost, we're going to talk about that at the end of this, is that not all molecules are going to exhibit emission spectroscopy. Most everything reaches its ground state through heat, right? How many objects glow in the dark? Not very many, right? So it's a pretty specific molecule that's going to offer emission spectroscopy. Let's see. How about this diagram? What was this trying to say? What good is it for in relation to what this class is all about? What good is that diagram? With the power that it's exhibiting here. What good is it? Andy, what good is it?
It can tell you whether there's an element like cadmium in a mixture of different metals.
Mm-hmm. It can tell you whether there's cadmiums in a mixture of different metals. How would you do that?
You look at the line, the emission spectra line.
Yeah.
And
That only cadmium has.
only cadmium has, which is circle.
Yeah. Yeah. And so you could tell that only cadmium's there. Could you tell how much cadmium's there, Mel?
You have to do a calibration
Do
curve.
a calibration curve. So does it have to be only cadmium? It could have been mercury. It could have been anything, right? So, well, anything meaning that it emits light. Now, one thing that we're going to see is, are these molecules or atoms, Andrew?
These are atoms.
These are atoms. Atoms emission spectroscopy is really sharp lines. Atoms are. Molecules are not, and we're going to see that. Molecules emission spectrum looks pretty much like an absorption spectrum. It's just shifted. It's all shifted to the red. So no, this works great, really, for atoms. Okay, which is kind of good because atoms don't work so great on the GC. Right? How much iron's in Granny's water? Well, you're not going to use the GC to figure that out, but you will use the AA. because iron's, you can use iron's absorption spectrum or its emission spectrum, right? It's the same. Okay, and then we got into some jargon, and I think this is where it got confusing. I think this is where I really started to lose people, if I haven't lost you already. It started out with singlet states and triplet states. There's actually a really easy difference between the two. In which state, Melissa, are the spins paired? And you say, singlet state. In which one? So by paired, meaning one spin up, one spin, yeah, so that's always going to be which one? Singlet state. If you have a, spin up, spin down, yeah, it's singlet state every single time. But if you have two electrons, they're not paired up, not spin paired.
Right. The triplets where I have both spin up, is that what you call triplet degenerate or triplet degeneracy?
Okay, now to get degeneracy, it almost depends on what the system is that you're referring to, because sometimes you don't see degeneracy until you apply a really strong magnetic field, and they call it Zeeman splitting and things. So to talk about degeneracy, I think we're really not going to worry about it. Degeneracy is just a fancy word for saying, hey, you've got the same energy in all these different states in the same energy. Okay, and so I really wouldn't go there right now. But the idea here is the difference between singlet and triplet states. Why we're talking about it? Because the book is, and I'm just following the book. Okay, but it's kind of important, because if we don't talk about these differences, we can't explain what process. If we don't introduce the words singlet and triplet states, we can't explain what process. Glow-in-the-dark toys. We can't explain glow-in-the-dark toys, because you see a glow-in-the-dark toy, that's an impossible occurrence. It can't happen. It's an unallowed transition. Why? Now that's a tough question. That's a really tough question. It's an unallowed transition, so that means on the molecular level, you have to wait around forever. And it will happen sooner or later. Just statistics-wise, it's very low probability, but if you wait around long enough, it'll happen. And on the microscopic world, a microsecond, a millisecond is a heck of a long time. That's data from Star Trek. So, what's so impossible about it? Singlet state to triplet state. For me, the idea is angular momentum. And it's a tough concept, because we ride bikes all the time and we don't even think about angular momentum. But it is a very funky, weird thing. You watch football and you have no problem at all seeing a great big guy run straight and have a hard time, people having a hard time stopping him. Whether if he moves fast or heavier, all the better. But angular momentum, having a bike wheel and just having it spin it and just having it stay at that angle, all on its own, that's a very weird thing. You don't expect it. So take that bike wheel. Its angular momentum is going one way, right? Sync it with another bike wheel's motion, pretty much going in the same way. That sounds like a pretty allowed thing. I can see that happening, right? Hook up those two bike wheels, they start going. But have one bike wheel's angular momentum going one way, another bike wheel's, it could be going the opposite way. It's a very different way. And get those motions to sync up. That's a pretty hard thing to do. I don't see it happening. But with statistics, that's the whole idea with quantum mechanics, is all these things are possible all at the same time. Some are more likely than others, and that's why we had to talk about singlet and triplet states, because they have different angular momenta. And if your excited state is a triplet state, your ground state is a singlet state, they can't jump from one to the other because of angular momentum. But, like I said, you wait around long enough, and you'll get the, what is it called? That emission spectroscopy. If it happens through emitting light, is it phosphorescence or fluorescence?
Phosphorescence?
It's phosphorescence. Fluorescence is the one where if the ground state is a singlet state, the excited state is still a singlet state, because then it's allowed. It happens on the order of nanoseconds or faster, a billionth of a second.
Fluorescence?
That's fluorescence. Okay. So these glow-in-the-dark toys again, they are phosphorescence. Okay, and then we're going to see this doesn't happen for all molecules. Emitting light is not a very common thing. Okay, so that's, see the triplet state to the singlet state, that was our phosphorescence. And then we had some terminology, right? And it's just unavoidable. To go from a singlet state to a triplet state, we called it intersystem crossing. Okay, we labeled a lot of those things. This is called a what diagram? Jablonski diagram. Yeah. So let's see. So try to be strong. Try to not look at your notes. See if you can name them. What was B?
Absorption?
B was absorption. Okay. What was, if B is absorption, what's D? Fluorescence. Good. If D is fluorescence, E is, oh, sorry, what is this? G. G is phosphorescence, because you see the triplet state, right? So H is for singlet and I is for triplet. Okay. How about, you see this A all over the place. A. Yeah. Vibrational relaxation. Is that emitting light?
No.
What's supposed to be going on with vibrational relaxation? Going back to the ground state. This is decreasing or increasing in amplitude. What I mean when it's going down A is with its vibrational relaxation. This motion, this oscillating motion, increasing, decreasing, or remaining the same. Has to be one of those. Decreasing. So it's losing energy. The frequency's staying the same, but it's losing energy. Losing energy to what? How? Getting converted into
Ground state?
heat, right? What is heat? Random motion, just more random motion, right? The more heat you have, the more random motion you have. What's temperature? It's a measure of heat. The more random motion you have, well, they call it thermal motion. The more thermal motion you have, then the more temperature you have, right? So it's just this random motion type stuff. How about F? There's that intersystem crossing, right? We got them all? Okay, but those are the main ones, I think. Okay. Here's a movie. Get to see movies in instrumental analysis. Oh, we need sound. There's a movie on the Jablonski diagram. You see what's happening with the molecule up there? You see all that? That would happen awfully fast, but we can pause it as it goes along here. Okay, so molecules can relax by vibrational relaxation and external and internal conversion. So let's see what will happen if another excited state with lower energy existed. So now you have this other excited state. So this light has to exactly match what? The ground state and... Yeah, and look at all the different excited states. I mean, you've got... This has to match one of these lines. It doesn't have to go to the... I don't know what else to call it. The ground state of the excited state. Does that make sense?
Yeah.
So you have these different vibrational... This is supposed to be a vibrational ladder. So the excited state, you're supposed to think of what changes in the molecule. If it goes from one excited... If it goes from the ground state, it's an electronic state, it's supposed to be changing the electron distribution, right? The orbital kind of thing, okay? And then the molecule gets excited to some vibrational state, right? Because there's your vibrational energy ladder, okay? So see, it's doing the stretching, bending. It's kind of vibrational relaxation, really fast. So it's just, it's slowly, it's losing energy to what? It's vibrational relaxation. Losing energy as heat, right? Because it's not emitting, it's losing energy as heat. It happens really fast, it says. And then for an electron to transfer to this 1, 2, 3, this fourth vibrational energy level of this excited state, see, it's not lined up. And lined up is pretty much just geometry. And it's not lined up with energy. So it's just not going to work. See, so internal conversion can't happen. So internal conversion was this way, right? Let's go jump over here. But it can't happen, so external conversion happened, they called it. Okay, so.
So what happens if they are lined up?
Then you get internal conversion, C. So the states have to be lined up. Or that's if they're in the same, singlet state. But if one's a singlet, one's a triplet, and they have to be lined up again, they call it intersystem crossing. I mean, it's, okay. Sketch a general absorption spectrum. Okay, you've had UV vis, so you have this thing on the screen. What's the x-axis there, Andrew, on that screen when you use UV vis? What was the x-axis? If you're doing a calibration curve. Yeah, wavelength. And what are the units? NM. NM is for what, Andy? Nanometers. 10 to the negative 9 meters. Okay. Roughly the size of what? An atom, right? How big is a molecule? They like to use the word angstroms.
10 to the negative 6.
Like, again, 10 to the negative 9, 10 to the negative 10, that area. 10 to the negative 8 in that area. Okay. Oh, we have to sketch it. What's the y-axis? Melissa, what's the y-axis on an absorption spectrum? Yeah, the signal, but technically it's absorbance. Absorbance looks better, I think. Okay. And then we're supposed to sketch it. Sketch, I don't know, we sketch whatever you'd like. Right? I don't know. It's definitely not this, right? Okay. We should probably say a general molecular. Because we're talking about a molecular compound. That's what I'm trying to get at. Okay, and then an emission spectrum. So let's say this is around, I don't know, just to put a scale on here, 500 nanometers. This is like 250 nanometers. And then an emission spectrum. Now, we haven't talked about even how to get an emission spectrum yet, but this will be wavelength down here again in nanometers. Okay. And we haven't talked about how to get an emission spectrum, but the point is it has to absorb energy, and then it's going to emit it, that molecule will. But notice how the energy that it's absorbed, right, here's your absorbance spectrum. If you just put this whole thing on its side, and then you could actually see the absorbance spectrum, the different little energy levels. See, take this guy, take this absorbance spectrum and put it on its side, all the way like this, and then you can see the energy levels. And pretty much almost their population, right? Look, this guy's got a lot, this guy doesn't have so much, right? So, what wavelengths are being absorbed and how much? Okay, that's your absorbance spectrum. So you pick a wavelength that where this guy absorbs, it'll get excited. It doesn't really matter which wavelength you pick, right? But you have to pick something where it absorbs. If you don't pick something where it absorbs, you're not going to get an emission spectrum. So 500 nanometers. And it seems to absorb really well there, so I pick 500 nanometers to have it absorb there. Okay, and I'm going to get an emission spectrum. So if my 500 nanometers is some big intense line, but the emission spectrum, look where it's at. It dropped all the way down here. The wavelengths are, this is a much less energy, but it hits the same, it hits these guys. It hits some vibrational levels, so there'll be some structure there. But the point is it's lower energy. And if it's lower energy, that means an emission spectrum, and it's detecting the light and all the wavelengths that are coming from this glow-in-the-dark toy or whatever it is. These wavelengths are going to be shifted to the, let's see, let's bring this up so you can see it. If I go to the left, that's shifting to the blue or to the red? Shifting to the blue, right? Because violet, Roy G. Biv, violet is the shortest. If I shift to the right, that's a red shift. Okay, so there's the question. Will this emission spectrum, and they always are, they're always shifted to the,
Right?
I don't know, to the red shift or blue shift?
Yeah.
They're always shifted to the red because it's a lower energy, right? Because look what they do. You have that vibrational relaxation. It happens every time, right? Vibrational relaxation happens every time before they emit. So your delta E is right here. It's always lower energy. So we're going to have to draw something definitely lower than, let's say we excite at 500 nanometers. Okay, so it's 500 is over here. And then, who knows? You can draw whatever you want. You know, it just has to be less than 500 nanometers. You don't know what it's going to look like. Okay. You know what I always thought is kind of weird is absorption spectra is really investigating the population in the excited state. You like to think of absorption spectra as, you know, ground state kind of stuff. But it absorbed there. How well did it absorb? Well, it absorbed a lot at 500. So that means in the excited state, man, it likes that 500 nanometer transition really well. But for emission spectra, that's really investigating the ground state, right? Because look at where it ends up, the vibrational levels of the ground state. So it's kind of the opposite of what you'd think. You'd think that emission spectra would be involving the excited state, because it's emission spectra. But no, With the emission spectrum, look, it drops down to the very first level before it emits light. So it drops it to all the vibrational levels in the ground state. It's kind of odd that emission spectrum investigates the ground state while absorption investigates the excited state. But anyway, I thought that's kind of odd. So how do you get that emission spectrum in the first place? Well, you have to have one of these. Does anybody know the story? Do we have one of these?
Here?
Yeah. Spectrofluorometer. We have one. It's about it's over there in the far corner by the new FTIR, but it's not hooked up,
Oh, the thing in the right corner is just there?
and it's just there, and it's called SPEX, S-P-E-X, fluorimeter, but it works great. We used it for the last research experiment we used it for was the scorpions. We scraped them off and we hooked up the HPLC to the fluorimeter because these scorpions glow in the dark. We wanted to isolate the compound, and we did. It worked really, really well. So why isn't it hooked up? It's not hooked up because it's very user unfriendly. And the consequences of not following the instructions to turn it on are huge. You have to push one button and then you push the other button. If you don't do it in the right order, you see a little puff of smoke in the back. And this about $1,000 lamp completely gets burned out. It's the stupidest way to design an instrument. I mean, how stupid can you be, right? You have computers. Push one button and let the computer take care of it. But, I mean, I wrote the log books, all that stuff, and then finally I can't do this anymore. So it's out. But I'd say it's probably the most sensitive instrument we have up there. And that's kind of hint as to things to come. But we talked about GC being narrow on what it can analyze. Well, this is really narrow. So, I mean, if it's not something like quinine, you're screwed. Okay, so how does it get in the emission spectrum? Well, you have to have a light source, obviously. All right? Okay. And then you have to have a sample. There's your sample. And this sample, you have to find out where it absorbs. So you put it on the UV vis first and get an absorbance spectrum. And this sample really absorbs blue really, really well. So I want to excite it with blue light. So, and you want a spectrofluorometer that's going to work for all compounds. So you don't buy one that can just give off blue light. So that means the spectrofluorometer has to have a what for that first box? There's an M. Monochromator. 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 A wavelength selector. You can see the slits, and there's a grating in there, and mirrors and stuff. Okay. So the excitation strikes the sample. The sample, what does it do? It'll absorb it, and then it emits light, assuming it's an emitter. It has that ability. And notice how the colors are red shifted or blue shifted. The colors are red shifted, right? So you're seeing these colors going all over the place, okay? And then it looks like it goes into another box, and only the orange is selected. So that means this must also be a monochromator. Monochromator. And then that orange light strikes a probably detector. What detector do you think it probably is? We gave it a name. Starts with a P. M. T. What do we call that? PMT. Photo. Had all those dinodes. Get a cascade of electrons, all from one electron. Converted light into electricity. Photomultiplier tube. Yeah, so that's going to be the detector. Okay. Because notice what we had when we drew our emission spectrum. We have all these wavelengths down here, right? 600, 700, whatever. We have all these wavelengths. So, and it measured the emission intensity. Forgot to write that axis on there. It measures the emission intensity of each one of those wavelengths. So you have to have a monochromator here that sits there and just scans all those emission wavelengths. So, and the detector detects the output from the monochromator. What's the intensity of each of those emitted wavelengths? Okay. With this spectrophlorometer, you can get an emission spectrum and you can get an excitation spectrum. So we talked about emission spectrum. Well, we should number these just to make it clear. Monochromator number 1, monochromator number 2. Emission spectrum, we drew it pretty much fix monochromator number 1 and scan monochromator number 2. Right? So that monochromator number 1, you set it to a wavelength where you know it's going to absorb, and then monochromator number 2 just scans all the wavelengths and get their intensities. How do you obtain an excitation spectrum? I think a word for this is the same as, it's an absorption spectrum. How can you get an absorption spectrum using a spectrophlorometer? All you do is you just switch these guys around, right? We're going to fix monochromator number 2. Fix. You know what I mean by fix? Just setting it at some wavelength. So you fix it, monochromator number 2, and it can't just be at any wavelength. It has to be a wavelength that it actually emits light. And then all you do is you scan monochromator number 1. And you get an absorbance spectrum. Because you're not going to see any emission if it doesn't absorb. So that's all it does. It scans all the wavelengths, monochromator number 1 does. It excites it at all these wavelengths, and it's just sitting there at that one emission spectrum. Hey, when are you going to emit? And the stronger the emission, well, the stronger the absorption was. So you get an absorbance spectrum. So you get 2 for 1 with these kinds of instruments. Emission occurs in all directions. Using the diagram to the right, appears all spectrophotometers. What is the angle between the excitation light and the detected emitted light? It's always, what does it look like? All right, it's coming in. It's coming in this way from the xenon lamp, and they're detecting it. That angle they're trying to say is the right angle, 90 degrees. Why? Because that we're talking about hardly any light at all coming from this thing. So the problem with scattered radiation is huge. So they're trying to minimize that. So that's why they just collected at 90 degrees, to try to minimize scattered. To try to minimize that scattered excitation light.
Is that sample cell supposed to be the cuvette?
Yes, except
Like the sides are all...
all sides have to be clear. All sides have to be clear. You can't have any frosted sides. I guess you could have one frosted side, right? You don't care about that frosted side facing away from the emission micrometer. But I think you don't even want that frosted side there, because you get all this scattered excitation light goes everywhere. It's really bright. And then if it has that frosted side, maybe it would bounce back and Yeah, so maybe it would reflect off. So I think, yeah, they want everything clear, really clear.
Is the xenon lamp is brighter than other lamps, or is it have a different spectrum?
This is essentially that lamp that's in the parking lot.
Okay.
They're really bright. And it takes a lot of voltage to get them to ignite. Maybe older parking lot lamps, because now they're getting into LED and sodium lamps and things. Okay, what characteristics?
Super, super bright? Or
It's extremely bright, and it takes a lot of voltage to get it to ignite.
Does it produce UV and
A
visible?
lot of UV.
A lot of UV.
I can show you one over here. We made our own. I don't know what the project was. We got all these funky ideas, and we wanted to. I think we wanted. It's called digestion. When you want to use the AA, you need to eat up all the organic stuff, right? Well, why not just shine ultra strong UV radiation on this material? It'll just eat the crud out of it, right? Except it's just really dangerous because it's UV radiation, right? But so what we did is we bought one of those parking lot lamps with this. It's in there, right? And we broke the outer glass shell because that's the UV shield. So now it has an inner shield, inner glass, but it's going to be exhibiting a lot of UV radiation. And it didn't really work out so well, but it's there in case we ever want to try it. Okay, well, what characteristics make a molecule a good emitter of light? So you've got a molecule. And there's a lot of different kinds of molecules. All right. And there's aromatic ones. I mean, draw your molecule. What makes it a good emitter of light? What characteristics? If you're going to classify and say, oh, hey, this guy has a chance of being a good emitter, you don't want a lot of what to happen in the Jablonski diagram. You don't want a lot of what? What do we call it? That internal conversion, where this vibrational relaxation is just all the energy goes into dissipation through heat. You don't want that to happen. And that happens really well when molecules are floppy. Right? They have all these vibrational modes, and they can flop and just flop, flop, flop. So when there's a lot of floppiness to a molecule, vibrational relaxation is all that happens. You need a molecule to be really what? Well, stable. They're all stable, I guess. Rigid. Really rigid. You have a really rigid, like a board. A molecule that's really rigid is going to be a fantastic emitter. So when you look at molecules, I don't know how you imagine this. If you can draw molecules like this versus drawing them like this. Which class of compounds are more rigid? Carbon chains are all this floppiness. That's how I picture it.
Yeah.
But that aromatic stuff, man, they get these alternating single and double bonds,
Yeah.
really stable. Man, pretty much all these emitters will kill you. They're all poisonous. They're all cancerous. They're aromatic. Okay. Well, not all of it's going to kill you. This lady's got makeup, right? Okay, so that's it.